Welcome to Shanti-Peace for Mathematics. In this video, we'll discuss regarding necessary condition for convergence of an infinite series. So that theorem is state like this: if the infinite series summation of un is convergent, then its nth term, that is limit of un, is always 0 as n tends to infinity. Now to discuss the proof of this theorem, we have already given that the series is convergent. So let the summation of un is converged to s, and its partial sum Sn is equal to u1 plus u2 plus un for every n in natural number. Then you just observe that what is Sn minus 1. The Sn minus 1 is a sum of first n minus 1 terms. So that will be u1 plus u2 plus un minus 1. And if I subtract these two terms, that means Sn minus 1 will left with just the last term, that is of un, because it is u1 plus u2 plus un minus 1 plus un, and this I have to subtract with u1 plus u2 up to un minus 1. So this u1 u2 up to un minus 1 term is cancelled out, only the term is left with un. So finally what we got, it is Sn minus Sn minus 1 is equal to un, and it is given that, or we have assumed that, the summation of un is converged to s. Also we have this limit of Sn is s as n tends to infinity, that is by definition of convergence series. Since the nth term is going to s, we also have n minus 1th term, that is a limit of Sn minus 1 is also as n tends to infinity. So what we got from this equation 1, if I take the limit into equation 1, so taking limit as n tends to infinity in equation 1, we obtain a limit of Sn minus Sn minus 1 as n tends to infinity is equal to limit of un as n tends to infinity. As per the definition or a property of limit, its limit of sum is a sum of limit. So as per that we can write down this is limit Sn as n tends to infinity is equal to limit of Sn minus 1 as n tends to infinity is equal to limit of un as n tends to infinity. But limit of Sn, as we have discussed, that it is s minus s, so that is limit of un as n tends to infinity. So therefore this will leave that a limit of un, that is the nth term of the series which is convergent, is 0 as n tends to infinity. So what we have observed here, if any series which is convergent, then its nth term, it has to be tending to 0, and that is a necessary condition for convergence. But this condition is not sufficient. That means the converse of this result is not true. So we should write as a note that the converse of above result is not true. That means if limit of un is equal to 0 as n tends to infinity, then summation of un may or may not converge. We'll give one example for that. So I'll give that example. We'll give this example. Suppose consider the summation 1 upon square root of n. Now here what you have, here we have un, it is 1 upon square root of n, and which will tends to 0 as n tends to infinity. So the nth term is going to 0. What we will prove, this series is divergent. That means here limit of un is 0 as n tends to infinity. But let us see what is Sn. To discuss it is a convergent series, we need to see whether the partial sum of that series is convergent or not. So Sn is, we know it is a first summation of the first n terms. So it will be u1 plus u2 plus un. Un is this 1 upon square root of n. So that is u1 is 1 upon square root of 1 plus 1 upon square root of 2 up to so on 1 upon square root of n. Now this I can say it is greater than 1 upon square root of n, because 1 is always smaller than n. So 1 upon square root of 1 is greater than 1 upon square root of n. So that's why 1 upon square root of 1 is greater than 1 upon square root of n. Same way I can say for 2 also. So 2 is less than n. So we'll have 1 upon square root of 2 is greater than 1 upon square root of n. Same way I can do the same term for each and every term. Will apply this property, and the last term I am writing as it is. This is 1 upon square root of n is coming n times because there are n terms. So from this what we can observe, it is Sn is greater than, what we can say, it is 1 upon square root of n, 1 upon square root of n, 1 upon square root of n, n times. So that will be n upon square root of n. And so this will be square root of n. So if I take the limit Sn as n tends to infinity, which will greater than limit square root of n as n tends to infinity. But this will gives me infinitive due to the square root of n is tending to infinity as n tends to infinity. But this limit is bigger than infinitive, so that's why this will gives me limit of Sn is also infinitive as n tends to infinity. So therefore what we can say, the sequence partial sum is diverge to infinity. So hence the series summation of 1 upon square root of n is diverge to infinity. So that means what we have observed here is again the things we have observed, that if summation of un is convergent, then a limit of un is 0 as n tends to infinity. But the converse of this result is not true. This is a necessary condition for convergence. But a negation of this result is true. What does it mean of a negation? If I have a statement P implies Q, then it is equivalent to saying that a not Q implies not P. This is an equivalent statement. That means what will be the negation statement of this statement is a limit of un is not equal to 0 as n tends to infinity implies non-convergence. So what is the things we can say it as a negation is a limit of un is not equal to 0 implies a summation of un is non-convergent. A non-convergence means the summation of un is either divergent or it is oscillating series. And that is also known as a zero test. So this test, it is known as a zero test. So what is, we have to check whether the series is convergent or not, or it is non-convergent. We have to just check that whether the nth term is going to non-zero. If it is non-zero, then definitely we can say that the series is non-convergent. The another name of the zero test is also known as nth term test. So both this name is well known for this test, that is this one. Its nth term is non-zero, then summation of un is non-convergent. Test the convergence of the series summation square root of n upon n plus 1. So here we have un is square root of n upon n plus 1. Let us see what will be the limit of this un. A limit of n tends to infinity un is limit of n tends to infinity a square root of n upon n plus 1, that is the limit of n tends to infinity. If I divide this n in the numerator and the denominator, then we'll have it is 1 upon 1 plus 1 by n. As n tends to infinity, 1 by n we know it is tends to 0. So this will gives me 1, and which is non-zero. Since it is non-zero, we can say that the series is non-convergent. As the series is positive term series, that means each and every term of this one is a positive. So we can say that the series is divergent because there is no chances of oscillating. Let us have some certain other examples. Test whether the following series are convergent or non-convergent. So we'll take this first example, summation of n square, n running from 1 to infinity. So you just see that here un is n square, and you just take the limit n tends to infinity. Un is limit n square as n tends to infinity is infinity. So by nth term test, the summation n square is non-convergent. In fact, it is a divergent because it is a positive term series. That also I can write. Let's have the another example. Summation n plus 1 upon n running from 1 to infinity. Here un is equal to n upon n plus 1 upon n. So if I take the limit n tends to infinity, un is limit of n tends to infinity, that I can divide numerator and denominator by n. So we'll have 1 plus 1 by n upon 1. So it will gives me 1, which is non-zero. So therefore by nth term test, the summation n plus 1 upon n is non-convergent. Let's have the another example, summation minus 1 raised to n plus 1. So here the nth term is minus 1 raised to n plus 1, and you can just take the limit of un will be limit of minus 1 raised to n plus 1 will be fluctuated between two limits. So I can say it does not exist. Since it is not exist and it is fluctuated between 1 and minus 1, the series is non-convergent. In fact, it is an oscillatory series. That we can see by its partial sum, because its partial sum is also oscillating between 1 and minus 1. That also I have discussed in my previous video. So here I can say that summation minus 1 raised to n plus 1 is non-convergent. Let us take one more example. Fourth one, summation minus n upon 2n plus 5, n running from 1 to infinity. So here un we have minus n upon 2n plus 5. And if I take limit of this un as n tends to infinity, that will gives me limit of minus n upon 2n plus 5 as n tends to infinity. If I divide numerator and denominator by n, then we'll have limit n tends to infinity minus 1 upon 2 plus 5 by n, and 5 by n tends to 0, so that will gives me minus 1 by 2, which is non-zero. So that's why we can say that by zero test or nth term test, the summation un is non-convergent. That's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or question, please drop down in the comment box below. See you in next video. Till then, bye bye, sayonara.